all the students. And in continuation of what we were doing yesterday, let me share the screen for you all. And this is to do with something that we had initiated yesterday. Okay, that the structure of the Earth. Now, an interesting thing to note is that when we are seeing these diagrams in front of us, they tend to be very geometric as such. And I would believe that the actual interior of the Earth will not be with so pleasant curved lines and so on and so forth. It would more be representing what I have put up as a thumbnail for today's lecture. And those who will be joining late, obviously when you move out of the lecture, you will see the thumbnail of this particular lecture today. And in fact, that also I would say is an artistic representation of the interior of the Earth. I believe it could be a more rugged as compared to the normal diagrams that we tend to see otherwise. This is something that we have to always keep in mind, that these are such things as far as the systems are concerned in geography, that we tend to at times take liberty with the diagrams as such, but we should always keep in mind that these diagrams are certainly not as geometric as they are shown to be. Then, coming back to the content we are speaking about, we have already spoken about this particular slide in detail, about the structure of the Earth, the right side of it, of your slide, and of course the left side of the slide as well. And beyond that, we also went into what is called what we have learned in that we know that the interior, the information, the knowledge that we have about the interior of the Earth is based on the seismic graphs that we tend to develop after earthquakes. And it's on that basis that the interior, we all know now, is divided into layers of different density, and it is the zone along which the density changes which is called as the discontinuity. Initially we had them between the crust and the mantle, and the mantle and the core, but now we know that within the crust also you have the Sial and you have the Saima, and you have the Conrad discontinuity between them. In the mantle, you have the upper mantle, which is a bit narrower than the lower mantle, and we have the Repeti discontinuity between them. Between the core, again, between the outer and the inner core, you have the Lehman's discontinuity. On the larger scale, we know that we have the Mohs discontinuity between the crust and the mantle, and obviously the Gutenberg's discontinuity between the mantle and the outer core is the scenario of it. Now, yesterday we just went into this diagram, and then we stopped the physical chemical properties. Okay, you'll see that it's interesting to note this point of the whole thing, that the average composition of the Earth is for half of the Earth's crust is made up of oxygen, and another half of the remaining half is silica. So 75% of the Earth is oxygen, silica, and oxides of silica, leaving a very small percentage for others to be distributed as such. Speaking about the mantle, you'll see that the density as far as the mantle is concerned is between 3.3 to 5.7 grams per cubic centimeters, and that for the core it increases. By the time it goes to the core, it increases to 10 to 13 grams per cubic centimeter. Okay, the continental crust of um, mm, the continental part of the crust, I would rather say, has a much lesser density as compared to the mantle and the core. That's between 2.7 and 3 grams per cubic kilometer, and the oceans which lie below the continents obviously will have a higher density, as far as which is between 3 and 3.3 grams per cubic centimeter as such. So one fact that we need to keep in mind is that the density is going to increase as I move toward the center of the Earth. In the sphere sense of it, you will see that the crust and of course the upper 100 kilometers of the, or say 70 kilometers of the mantle, is known as the lithosphere, which is a brittle solid as such. The asthenosphere is which lies below that, and that's going to be called as the ductile solid. And then you have the mesosphere, you have the outer core, and of course you have the inner core as such. Okay, then we come to something which is very interesting, because what we are now going to do is, while in this diagram here we saw the composition of chemical composition of the crust only, now we are going to compare this with the entire crust. Now there's a very interesting point to note about this, but then we'll just discuss about it earlier, and then we'll go to that interesting point as such. That we have already spoken about the crust, but we'll once again run through it, because the percentages would differ a bit. And in fact, here you'll see, you add up oxygen and silicon, it is moving to exactly 75%, and you add another 8%, that's going to be 83% of silica, aluminum, and oxygen. And of course the remaining are going to be, say, you add another 5% of iron to that, four of them make up 90% of the crust. And then you have magnesium and calcium and potassium and sodium and potassium are the salts, and all other components make up the remaining 2%. Now when we are going to compare this to the entire earth, there are some switch in positions that tend to happen around the entire earth as such. When you speak about the iron, look at the iron here. When we speak about the entire earth, it consists of 35% of iron, as compared to only 5% of the iron in the earth's crust. So all that iron that we mine on the crust of this planet is just 5%. You have much, much, much more of iron as you go towards the interior, and it's going to be in large proportions as such. Oxygen, you'll see, while iron has moved to first position as far as entire Earth is concerned, oxygen has slipped down to the second position, and now oxygen, iron together are constituting around 65%, and another 15% of silicon and 13% of magnesium added to it. You'll see that 60, 70, 80, nearly 90% of this again is made up of only four major components: iron, oxygen, silicon, and magnesium. Now, as far as oxygen here is concerned, why is it, how is it that the percentage drops? Uh, we have to remember that oxygen is an element which is a gaseous element, and it's a very reactive element, and it reacts with material which comes in immediate contact with it. And so obviously the penetration power of oxygen as far as the interior layers of the earth is concerned is less. So it's only a bit more, say you could have a bit more of it due to degassing, as it is called, in the mantle and some parts further in as such, but that would be literally trickles as such. Then you'll see that silicon, which is 28%, is nearly half of it. Now, what does this mean, that oxygen and silicon 47 and 28% in the crust, and only 30 and 15% in the entire earth? That means you have a higher percentage of concentration of these two material in the crust, as against a very high percentage of iron as compared to the crust, when we are speaking about iron in the entire earth is concerned. Magnesium, again, you'll see only 4% in the Earth's crust, but makes up 13% as far as the interior is concerned. You'll see that magnesium tends to ignite. Magnesium is something which is used in fireworks, to the best of my knowledge, and that's why you'll see that as you go towards the interior, you're going to have more of magnesium. You did not have nickel at all as far as the Earth's crust ranking is concerned, but you have 2% of it, because we know that we abbreviate the core as NiFe, nickel and ferrous. Nife, some people call it Nife, some people call it knife. But what it explains is that you have a higher percentage of nickel, which is a heavy element in the sense heavy in weight. Okay, it goes toward the center of the earth. Sulfur, again, though we have a lot of volcanoes as far as the Earth's crust is concerned, it does not rank in the first 8, 9 elements. But overall, you have 2% of sulfur in the entire Earth. So obviously, you're going to have more sulfur in the interior. Calcium, on the other hand, is only 1% in the entire Earth, but you have 2%. That means crust has more of calcium. No wonder majority of the surface animals are going to use calcium to build up their skeletal systems. Okay, all the say animals belonging to the vertebral the class or phylum. I'm not very clear about that. Vertebra, and you'll see that the whole skeleton system is made up of calcium. An interesting note here is that while land animals and animals who are going to be there in the surface layers of the water will be using calcium as far as their body building, skeletal building is concerned. When you go to the deeper waters, of course, the pressure of the waters, calcium otherwise is a very brittle substance, isn't it? Element, you could say. And as a consequence, as the animals are going to dive deep, the fish, let us say, and other organisms are going to dive deep, their skeletal system could be under the pressure of the water. So you'll see that in deeper waters, animals tend to use silica as far as their structural system is concerned, more as compared to calcium, is one thing that we have to keep in mind. And then you have aluminium, which is 1%, which was 8% in, rather is 8% in the Earth's crust. So it's a lighter element. So obviously it has been thrown towards the outer side of the Earth, thus leaving a very small amount when we speak about it in the entire Earth. And others, of course, is 1% only as far as entire Earth is concerned. Others involve 2% as far as the Earth's crust is concerned. Now, I would say that yes, we have explained a few things, but these figures have to be taken with a pinch of salt. Why do I say that these figures have to be taken with a pinch of salt? Basically, because left side of your screen you have the elements which make up the Earth's crust, and right side are the numbers that make up the entire Earth. Now, obviously, percentage wise, though there is a difference, I could point out a few of them which are very close to each other. Okay, let us say calcium is half of an impression could be that say a significant amount, half of the calcium of the Earth's crust is the Earth, rather the crust makes up the half of the calcium content, rather or with regards the entire Earth. And you could similarly compare the percentages in the crust and the entire Earth as such. Having seen this, okay, as I said, what is that pinch of salt? An interesting and important thing, I would rather say more important thing that we have to understand is that when we speak about the fraction of the Earth here, okay, it makes less than 1% of the mass of the Earth. The mantle and the crust literally make 99 point some more percentage of the whole fraction of the Earth. It's only 1%. So actually, so you're going to see, you'll see that these proportions are nowhere a match to each other when we compare it. It's only for academic purpose that we compare them. What I mean to say here is, while we say 5% of oxygen, 5% of iron here, and 35% of iron here, it's going to be huge percentage of iron that you're going to have in the interior of the Earth. On the other hand, you'll see that if I find something more here and something less here, say for example, you have been speaking about sulfur and you are speaking about nickel, two percentage points each, and you hardly find them here. That doesn't mean that it's going to be less. It's going to be a huge percent. You'll see. Remember that Earth, entire Earth occupies nine. These are split into 99 percentage mass of this particular planet, while these numbers are occupying only less than 1% of the mass of this particular planet is concerned, is something you have to remember all the way through. Okay, because if somebody remembers only that these numbers, then that could be leading to an misinformed information that you could pass on to others, or you could recollect on your own end. As far as the state of these three layers is concerned, crust is basically broken rock, mantle is near to plastic, and core is semi-liquid, in the sense that the outer core is liquid and the inner core is solid. As far as the depth is concerned, the crust is between 30 and 40 kilometers. The next 3,000 kilometers is mantle, and another 3,500 kilometers beyond that is the core as such. This is what we are referring to here. And then density, we have already said that the crustal density is very less, 2.7. By the time you reach the core, it's very, very high. It's nearly 12 to 10 to 12, and leaving the mantle between 3.5 and 5, 5.5 grams per cubic centimeter as such. Having said this, you'll see that again these are mathematical numbers, and please don't be confused. Okay, normally they phase out. Okay, they phase out because why can we confidently say that these the densities phase out when you move from the interior to the out of this particular outer crust of this particular planet? The fact that the Earth has gathered its size and mass over the period of time, it has taken millions and hundreds of millions of years to form into what we are seeing as the Earth. So, obviously, while this whole process was happening, the denser material got caught into the central parts of this particular planet, and the lighter materials then covered the denser material eventually. So outer parts are going to have lesser density, and the inner parts are going to be having higher density as such. Chemical composition, you'll see that we have already seen that a lot of oxygen and silica is found in the say you've just seen here 47 28. So most of it is going to be oxides of silica. And then as you go into the interior, you'll see that the oxidation of silica is more. With that, you're going to have ferrous and magnesium, which again we have seen here is has increased to 13%. That's basically because of a lot of magnesium in the mantle. And then towards the center, you have a lot of iron and you have a lot of nickel. Okay, so you'll see that nickel makes up 2%, and iron obviously 35%, a staggering 35% as you go to the interior of the Earth. Temperatures in degree Kelvin. Now, students of science should be in a position to know what degrees Kelvin is. Later on, when I'm going to interact with you all on Google G Suits, we could actually go into the details of what is the difference between centigrade and Fahrenheit and Kelvin. Many students I've seen, they learn chemistry, but they don't know the basic differences between what is a centigrade, how does it differ from a Fahrenheit, and how does Kelvin make its say how is Kelvin totally different to all the other two as such. It's a very interesting fact to note how these three systems of calibration, or rather these systems of measuring of heat energy, came into existence as such. Okay, any of y'all who searches the net could find this for us, and you could place this in as a point of record on the WhatsApp group as well. And the next aspect, okay, from chemistry to physics, the pressure. Of course, both of them apply in both the senses, but then to make some sense out of what we are discussing, or to give us some amount of absurd logic, I would say, of the pressure on the surface is or the crust is around between 1 to 1000 atmospheres. Now, what does the pressure of an atmosphere mean? Okay, we all know, and of course we are going to learn this in our second semester, that in climatology and oceanography as such, that the earth is enveloped with a layer of gases which is called as the atmosphere. Now, if I take a space of around 1 feet to 1 feet, a square of 1 feet to 1 feet on the surface of this earth, and then I collect all the gas layers that I'm going to have all the way up from this particular point as such. This point as such, what happens is this huge layer. Okay, we I think we spoke about it, or no, I'm not very sure, but I think yes, atmosphere is around 480 kilometers is what geography understands and studies. So all that gas packed into those 480 kilometers, and that say pillar of let us say 1 feet by 1 feet. Okay, the pressure of the gases in the 480 kilometers, actually if you remember we said that 99% of it is within the 30 kilometers. So even a pile of 30 kilometers should be, a bar of 30 kilometers should be fine. But let us say up till 480 kilometers, if I take it and I measure the weight of it, the pressure of it on the surface under the force of gravity, that is going to be called as 1 atmosphere. When it doubles, it's going to be 2 atmospheres, further doubles 4 atmospheres, and so on and so forth. So you'll see that those who have been those who have learned swimming, and normally you dive under the water, you feel the pressure of the water on your body when you're swimming in the lower layers of water as such. Just imagine when we go further down, as far as these the ocean waters are concerned, the average weight of the water is obviously going to increase, and thus the atmospheric pressures also increase. Yesterday we were speaking about how deep man has gone. One limitation that keeps man from diving deep even after using a lot of technology is this particular factor, that the pressure of the water, etc., is so huge that it could just crush away anything. Now you would say, sir, we are on the surface of this particular planet, and we hardly feel the pressure. Obviously, science students should not be saying this, basically because we have studied this as a part of our experiment in our school days, that that's basically because the pressure outside around us and the pressure inside our body are balanced, and that is why our body doesn't crumple down. We have seen that experiment, that if you take a tin container and you extract the air out of it, the container will shrink, basically bowing down to the pressure that is generated out of the atmosphere. So even one pressure, atmospheric pressure, is huge. It increases to 1,000 atmospheric pressures by the time you are at the boundary of the crust. Then you enter the mantle. Within the mantle, from 1,000 atmospheres, it increases to 1 million atmospheres. Just imagine, 10 and 6 zeros, 1 million atmospheres is the atmospheric pressure in the lower parts of the mantle. Let us say the lower mantle as such. And as if this is not enough, you'll see that toward the center of the earth, uh, the pressure is so huge, that, 1 million atmospheres, that it actually say liquefies everything. And that's why it is believed that the uh, outer core is in a liquid format, and the inner core, because it's further pressurized, you'll see that it concentrates to form a solid structure as far as making up the central core of this particular planet is concerned as such. So that is as far as these few things that we needed to understand. We'll move ahead. A few more things that we need to get to know is this part first. Okay, the physical properties, the hydrosphere, then the asthenosphere, the lithosphere, or the solid and brittle first 100 kilometers as such. And then the mantle is also, because it's in the middle, it's also called as the mesosphere. And then the core further divided into outer core, which is a liquid, and inner core, which is a solid as such. So uh, say it's going to 2,900. Actually, it looks like a 2,000, but it's 2,900 kilometers, beyond which the inner core is reached as far as sorry uh, the inner core is reached when you are at a distance of 5,150 kilometers towards the interior. And the center, we all know, is 6,413 kilometers. 6,400 should be fine to understand. 13, some say 37, and so on and so forth. Coming to the density, once again, you'll see that it starts at as low as 1.03 as far as the oceans are concerned. It goes dense by the time you come to the crest. It's 2.7. Boundary of the crust is 2.7, and then it moves into 3.3. Gradually, you will see that it will increase to 3.6 and 4.3, and reaches to 5.7. And say higher the density, of obviously darker is going to be the color as far as the rocks are concerned. The crust is made up of lighter colored and low density rocks. as such. So, as I'm going to enter the core, it's going to be all of iron and nickel. The very feeble percentage of other components here. It increases from 9.7, and in fact, this diagram you'll see it shows it's nearly uh, 16 uh, grams per cubic centimeter as far as the center of the earth is concerned. Very, very high density. These numbers will keep on varying. Okay, let me tell you, the different diagrams you pick from different sources, these number will vary. And you can see that the radius of the earth, or the distance to the center of the earth, is 6,371 kilometers in all. Then a few more things that we need to understand. Okay, density we have already seen. It's only that they have now given us in a top bottom form. So density at the top of that particular layer and bottom of that particular layer. So you start at 2.2 and you end at 2.9. That's the crustal limit of density. 3.4 to 4.4 is the upper mantle. 4.4 to 5.6 is the lower mantle. 9.9 to 12.2 is the outer core, and inner core. 12.8 to 13.1 is the density as far as the inner core is concerned. The thickness, we all know, 30 kilometers. The crust, again, some references you'll find it up to go up to 40 kilometers as such. But this change of 10 kilometers is hardly anything when you go into the inner parts, inner layers as such. The upper mantle is 720 kilometers. And that also indicates the fact that most of the earthquakes that we are going to study in times to come, they originate within the upper mantle. You'll see that the deepest of the earthquakes don't go beyond 800 kilometers deep as such. So the origin is more in the upper mantle rather than the layers which are going to be further interior as far as the earth is concerned. Lower mantle, you'll see 2171, outer core 2259 kilometers thick, and inner core is 1200 kilometers thick as such, making it around the thickness around 6401, which also can be identified as the radius of this particular planet as such. So this is a lot of information covered as far as the interior of the earth. Let us see if we have any more information, and we would go into that as well, sorry. So if we are to enlarge this, okay, you'll see that you have a lot of convective cells that keep on working as far as the interior of the earth is concerned, and that keeps these plates on the plates, the crust which is made up of plates of earth, to fracture and move here and there as such. Okay, so you'll see that plumes, I would rather say, plumes of molten material are released from the outer core, and they travel through the mantle and they try to come up. As they are going to be released upwards, you'll see that the hotter material comes up and the heavier material, the colder material, goes down, building up what are called as convective cycles. Okay, and while these keep on moving in circulation in the interior parts, okay, the crust which is riding about this, okay, you will see the plate movement on the surface. We'll come to study of that in when we go into the details of that as well. Coming to the temperatures as such, you'll see we already have spoken about the temperatures in degrees Kelvin. Now this is degrees centigrade. You see that the temperatures rise up to 2000 degrees centigrade as far as the upper mantle is concerned, and it increases all the way to 3000 degrees centigrade as far as the outer core is concerned. Lower mantle is concerned, and 3800 to the outer core, that's a liquid thing, is concerned. By the time we go to the central core, you'll see that the temperatures are nearly 6000 degrees centigrade. A huge amount of temperature, let me say here as such. So that's about the temperature in degrees centigrade also. And let us move ahead. Okay, we have been discussing about the interior of the earth and the study of the layers of the earth. How does this actually take place? This, you'll see, it's always discussed that the study of the interior of the earth is extensively and heavily dependent on studies of seismology, that's earthquakes as such. And I purposely brought up a paper here which discusses exploring the interior of the earth using seismology. Those who are interested could just note these details down, and you could search for it on internet as well. Okay, what I've done is I've cut this up and I've put it up as a larger part of the diagram here. Okay, you'll see that when an earthquake happens, it is basically a lot of shakes as far as the crust is concerned, and these shakes are measured in waves, and these waves is in fact the direction in which the energy transfers itself from one point to the other, and that is why they tend to be classified into different types of waves. Okay, so on a broader scale, you would say that they are classified as body waves and surface waves, two of them each, and then you will have the primary waves and the secondary waves as further parts of the body waves, and the love waves and the rally waves, which make up which travel through the surface as such. And of course, it speaks about how they travel, also how fast they travel as such. Okay, you'll see that the first of them to strike and to be experienced are the P waves, and that's why they are also called as the primary waves. Now, what is the direction of propagation, etc.? Propagation and direction of wave movement is already studied in physics, but we are going to look at it from a different point of view as far as geography and earthquakes is concerned. Different point of view. The actual functioning is going to be the same, let me tell you. Then you'll see that as far as these waves are concerned at this point. Okay, what I mean to say is, say, just look at these dark lines here. Okay, at this point away from, at this distance away from the focus of the earthquake is concerned, you'll see that it will hardly take any time to reach this particular point. Okay, this particular point, you'll see that it will take at least 10 minutes. For traveling further, you would say this particular point, the earthquake waves will be felt only after 15 minutes, and so on and so forth. As you go away, you'll see that the time taken for, obviously that's a basic rule of science. What is interesting is to note the shadow zone. Okay, you'll see that somewhere between 100 degrees and 140 degrees from this particular point. Now, here again, I wanted to speak about a few things, but let me not confuse you more with this now. I will take a more easier diagram to understand what I wanted to explain to you all about the shadow zone and the reference of the shadow zone with regards the focus of the earthquake is concerned. Okay, sorry. How do the earthquakes look on a seismograph? Okay, you'll see that the P waves, the first to arrive, are in this particular way. The secondary, this S stands for secondary, and then these are the surface waves. Okay, so secondary waves will follow, and surface waves are the last to arrive. But you'll see that though they are the last to arrive, uh, they obviously are very destructive, is something that we need to understand at this particular level as such. Then we come to this particular diagram. This is the epicenter of the earth. Okay, and at immediately below the epicenter, 90 degrees below the epicenter, you're going to have the focus. And as I said, that earthquakes normally are not very deep rooted as such. The maximum notings are taken is 800 kilometer, not beyond that as such. So earthquakes are going to happen more toward the surface. The adjustments in pressure, etc., are going to happen, but the shocks are sent all through, and the shocks travel in different ways as such. Once again, you'll see that, as I said, between 103 and 143, okay, we are going to have a shadow zone as far as the P waves, primary waves, are concerned, and a larger one is seen as far as the secondary waves is concerned. 103 to 180 is how this stays to be blank as such. Okay, these obviously, this is the section where you have the refracted P waves as such. Now, what all this is, we'll come to that. But a point that I wanted to clarify, normally you'll see that the diagrams which are going to explain a focus, the diagram which is going to explain you the epicenter, and the diagram which is going to be explaining you the shadow zone, all of these diagrams anywhere you'll find in this particular way. Now, students with a proper logic will understand this, but then some confused students would find, and in fact, okay, this statement comes from an experience. Students have been asking me that whether earthquakes happen only at the North Pole. Let me tell you, this is a relative position. Okay, earthquakes can happen anywhere on the surface of this planet, but for the purpose of understanding what they do is they shift the epicenter of the earth to what I can say a 12 o'clock position, so that we can understand and explain other things with regards clock measurements or with regard degree measurements as such. So if I put the earthquake at zero, then I could easily calculate that at what angle I should be expecting the P wave shadow zone, the S wave shadow zone, and so on and so forth. So I again repeat that earthquakes can happen anywhere on the surface of this particular planet. The only thing is that it is a matter of sheer convenience that that point, okay, wherever it happens, okay, let us see here, okay, earthquakes can happen anywhere, but what we do is we shift that particular point to this, so that under explaining other things is going to be or understanding other things is going to be easier. Okay, so that's a very important point to be noted. Okay, then we move ahead. I think yeah, you will see here, I don't know. This was a GIF diagram. I'm supposed to be having this, but then it's not moving. Anyway, so we are going to have a point here wherein uh, the earthquake gets initiated. Okay, so that's called as the focus. Again, let me tell students that students normally confuse themselves between a focus and an epicenter. Focus is from where it starts. Epicenter is the point exactly at 90 degrees from the focus on the surface as such. So it is always said that as far as these traveling of waves is concerned, the primary waves will strike the epicenter the first, and then it will keep on traveling to the other areas around the epicenter as such. So that's why, and that makes the epicenter an important aspect. Now, what should you be looking around when you have an earthquake? What should cause an earthquake as such? So you'll see that here a faulting has taken place, but the earthquake will not start here because the force which is creating the tension is somewhere way down into the interior. So that's going to be your focus, and the wave fronts are going to move in a circular way away from the focus of this particular fault line, fault plane, I would say. What you're seeing, the black line is fault line, but the whole surface is going to be the fault plane as such, and that point is going to be the focus, and the point exactly above it is going to be the epicenter. Okay, so I hope you don't confuse yourselves as far as the difference between an epicenter and a focus is concerned. Okay, then these are the various ways in which the earthquakes are measured. The most common way is the scale used is a Richter scale. Now, let me tell you that a Richter scale is something that is measured in a log scale. Now, my question for you all, okay, if you can find out a simple answer, I don't want technical definitions of what is a log scale. Okay, all of us have done log scale in school level. If a no, layman asks you what is a log scale, how are you going to describe it? Is what my question is. I want students to respond on this and into our the uh, WhatsApp group. Sorry. So magnitude and description uh, and frequency wise as such. Okay, you'll see that you hardly feel earthquakes which are micro and minor at first level. Okay, only a few people feel them and there is no damage. You'll see that around millions happen as far as uh, those with a magnitude of less than 2 on the Richter scale is concerned. You'll see that many times you just hear a sound somewhere and you just don't know where that sound had come from. That sound goes thadam, and many times it's obviously some industrial activity happening somewhere, but at times it happens from the interiors also, but it hardly disturbs anything on the surface, and that's why they're called as normal micro level, and you have them millions happening per year. Minor is something that happens over a million times a year as such. Okay, then a minor at a bit higher scale, small people feel them objects inside can be seen shaking. So you'll see that if I have a liquid somewhere here, I will just see it shaking. If you see something shaking without a reason, then that could be an impact of a minor earthquake as such. You could have again them around say 100,000 of them, okay, in a year. Light is around 4 on a Richter scale. Okay, light earthquakes. Okay, most of the people feel it. Indoor objects shake, and you'll see that the ceiling fans start dangling, the blades start dangling, and so on and so forth. We have around 10,000 to 15,000 of such every year. All these are every year. Let me tell you the frequency. Okay, light ones are around 5 to 5.9. Moderate, they're called as moderate, but you'll see that this is the scientific measurement. Okay, the destruction scale is much different. Okay, this is the normal scale. Okay, now if you're going to construct houses which are not solid enough, even a moderate or a light earthquake could destroy them, and then your human loss of life and property is going to be huge. So that's a completely different set. We are just studying the natural aspect of it, we are studying the scientific aspect of it. 5 to 5.9 are actually listed to be moderate, can damage or destroy buildings not designed to withstand earthquake. Everyone feels it, but then if a building is not constructed on the basis of sustaining earthquakes, then the building could be damaged. 5 to 5.9, and you have around 1,000 to 1,500 earthquakes of this magnitude every year. Then moving to 6 to 6.9, these are strong, and you can experience the shaking even away from the epicenter. It surely damages buildings, even if they are moderately sustaining to earthquake technology as such. And you have around 100 to 150 of them every year. So you'll see that it's again, this is also decreasing in an log scale. This is also decreasing in a log scale, you could see. Okay, I give you another hint to try and understand what exactly a log scale means. A major is 7 to 7.9, widespread damage in most areas. 10 to 20 happen every year. 8 to 9 is great. Okay, widespread damage, and so on and so forth. About one per year in some part of the on the surface of this planet. This does not necessarily happen to be there on the land. It could happen under the ocean also. And the moment you have it happening under the ocean, any type of earthquake, you'll see you should be expecting a tsunami out of it as such. And then 9 to 9.9, severe damages to most buildings. This happens in 1 per 5 to 50 years as such. And finally, 10 is massive. We have never recorded such types of earthquakes. Massive would basically mean the land crushing and crumpling just like a wave of water. Okay, you'll see that land will roll up like a wave and fall down as a wave. If ever we have a earthquake to a magnitude of around 10 on the Richter scale as such. Okay, these are obviously the sorry. We all know what this is. This is a seismograph. Okay, and you have different types of seismographs. Okay, and the ways in which these are recorded. These are obviously very advanced ones. Here you can see. Okay, then we have another way of looking at it, and however we don't have time for that today. We'll continue with trying to understand this when we meet tomorrow. I want you all to try and understand that when we say it's on a Richter scale, what exactly does a Richter scale is, and Richter scale is a log scale. What does a log scale mean? Let me give you more hints that your pH value is also measured in a log scale. Sound pollution is also measured on a log scale, decibels log scale as such. So I think these hints should be more than enough. And I want you all to work on what exactly a log scale should mean. And let us see if you are able to answer me on the group as such. I'll be ending it here. And that's all I would say we have for the day. We'll continue with the same thing tomorrow. If you have any questions, you can post those questions in the group. I'll try to answer the questions on the group as such. As far as college offline college is concerned, it is believed that if things don't turn adverse, next Monday onwards, we are going to have 100% offline college. So you can start planning accordingly. Okay. Of course, this is not authentic, but that's the feeling that I have, that Monday onwards, we could be having 100% offline college, theory as well as practicals. So that's all for the day. We meet tomorrow at the same time, and same time, that means 10:20, and we'll finish off. Let us see how much we can finish as far as studying the earthquakes and the interior of the earth is concerned. That's all. I'm ending my broadcast here.